Hi, I'm Daria Lane with the Naval Information Warfare Center Pacific, and this is nanosatellite tracking using passive radar retroreflectors. So traditional non-cooperative tracking systems, such as the Space Surveillance Network, use electro-optical telescopes or radar systems to attempt to track objects on orbit. But most of these systems were designed when there were very few small satellites deployed. Commercial services have recently augmented the existing government capabilities, but they'll also have difficulty tracking the large number of small satellites that are coming online in the next few years. So in order to maintain good space domain awareness, cooperative tracking systems where a satellite aids the tracking system are required. There have been multiple small spacecraft cooperative tracking methods proposed and demonstrated. And some of these include the extremely low resource optical identifier, which uses optical transmissions from the satellite to ground telescopes. CubeSat identification tag uses a radio interrogation and a response system that's coupled with large ground-based antennas. And the enhanced low-power transponder, which transmits the satellite's GPS coordinates to the ground via RF, and then uses the radio signal characteristics to calculate the associated orbit. A summary of the comparison of the current small satellite tracking technologies is given in the table here. So by having multiple options, spacecraft developers will have the ability to make appropriate system trades and find a solution that works and meets their mission requirements. So today I'll be discussing a hardware solution that NIWC has developed, known as the Nanosatellite Tracking Experiment, which utilizes passive radar retroreflectors to detect and track small satellites. So we have developed a radar retroreflector that may be easily attached to the external surface of a small satellite. It will allow radar systems on the ground that are responsible for tracking objects in space to much more easily detect and track small satellites. This is a hardware-based approach to improve the detection, tracking, and identification of small satellites, both for space situational awareness and for space traffic management. So other tracking methods typically use active transmitters to identify and locate a host satellite. But these transmitters typically require power and often need to be integrated within the spacecraft electronics. In addition, they also radiate RF energy, which can cause interference, and need a ground infrastructure to support them that will also need to be integrated into the space object tracking infrastructure. The nanosatellite tracking experiment retroreflectors are completely passive. They do not require any power. And they're thin, lightweight panels that attach to the unused external surfaces of a small sat, and they minimize the overall impact to the small sat as a whole. The retroreflector devices will also function even if the spacecraft loses power while it's operating on orbit. So the NTE devices are attached to the external surfaces of a host small sat. And then when the host small sat passes over the ground-based tracking radar, the radar cross-section measurements are collected. This data is then correlated with the orientation and attitude information from the small sat in order to quantify the improvement in RCS with the retroreflectors on board. So the ground-based space object tracking radar that's being used with NTE is the MIT Lincoln Laboratory Haystack Auxiliary Radar. And while the passive retroreflector devices have flown on orbit multiple times, we're presently developing a technique to modulate the reflected radar pulse in order to support a unique identification capability. So a retroreflector essentially reflects incident electromagnetic energy, such as radar pulses, back to a source, giving a strong return that's independent of aspect angle. So these passive retroreflectors, as I mentioned, fit a standard 1U sized CubeSat panel, and they have a flat form factor for easy attachment to the external surface of a spacecraft chassis. And the antenna elements themselves are small enough in the KU and X band that they can easily be integrated into a small sat. So we developed a planar Van Atta array retroreflector design that's specifically tuned to the operating parameters of the HAX radar. So a retroreflector will return most of the energy of a received radar pulse back to the radar set, which greatly improves the observed radar cross-section of the object regardless of the orientation. The radar return of a flat metal plate drops off significantly at only a few degrees from normal. Retroreflectors provide a similar return at normal, but the drop-off is much less comparatively. Retroreflectors vastly improve the radar cross-section response of small satellites at all aspect angles other than that normal incidence. So with these strong radar returns at all angles, the detection rates and the tracking of objects on orbit is greatly improved. The Van Atta array, it uses an array of antenna elements connected by transmission lines in pairs that are symmetrical about the center of the array. So the incident RF field that is received by each antenna feeds a corresponding antenna via that transmission line where it is then re-radiated. The phase distribution of the re-radiated fields will be reversed as a result of the feed structure, which causes the wave to be re-radiated in phase towards the incident direction. The transmission lines that are between each of the pairs of antenna elements are phase matched, and that's in order to propagate a reflected wave in the same direction from which it was received, as shown in the figure on the left here. Each of the paired antennas is able to both transmit and receive simultaneously, producing a propagating wave towards the direction from which it was originally transmitted. The phase-matched transmission line lengths themselves between the paired antennas are absolutely essential to producing the redirected waves. So we've developed a 64-element Van Atta array design operating from 15.7 to 17.7 gigahertz with right-hand circular polarization that fits a standard 1U cube satellite panel. With pairs of slot-fed dipole antennas that are arranged in 8x8 formation and connected via phase-matched transmission lines that are symmetrical about the center of the array. As I mentioned, the design's optimized for detection and tracking with the MIT Lincoln Laboratory HAX radar. And the middle figure here shows the HFSS model of the NTE antenna design, and the fabricated NTE panels are shown here on the right. Far-field RCS measurements were taken following fabrication of the NTE devices after they were mounted on a 1U cube satellite model, and that was using an anechoic chamber here at NIWC Pacific. So for all of the RCS measurements, a flat metal plate of 10 by 10 centimeters oriented normal to the test emitter was used for reference. And KU-band conical horn antennas, circular waveguide mode transistors, and KU-band linear to circular polarizers were used in monostatic configuration in order to transmit the KU-band RHCP signal. So for the two test cases I will discuss, the cube satellite model was rotated 360 degrees about the vertical axis, and measurements were taken, then taken in the anechoic chamber. In this first test case, the 1U cube satellite model was oriented so it would rotate from face to face in the vertical axis, as shown here in the picture on the left. The middle plot shows the radar cross-section response of the cube with the NTE retroreflector device as it's rotating about the axis 360 degrees. The right plot is the RCS response for the same 1U cube without the NTE retroreflector device mounted on board. As you can see here, there is a considerable difference in the RCS responses between the two. In this second test case, the 1U cube model is configured so it'll rotate from face to face orientation in the vertical axis, as opposed to face in the previous slide. So similar to the last chart, the middle plot shows the RCS response of the cube with the NTE retroreflector device, and the right plot is the RCS response for the cube without the retroreflector. So for the measurements of the 8x8 NTE array, They show a radar cross-section improvement of around 20 to 30 dB when the aspect angle of the CubeSat model surfaces at any angle other than normal to the incident radar pulses. At normal incidence, there is no improvement in the measured response, but that's as we expected. So following fabrication and the measurements of the respective radar cross-sections, the NTE retroreflector devices completed full spaceflight qualification and acceptance testing to include thermal vacuum, shock, and vibe testing. The NTE devices have since flown on multiple Department of Defense and commercial space missions. So one of these missions is Star 3, where 3 passive 1U satellites were used as calibration and characterization targets. These were developed by NIWC and launched in December of 2018 aboard SSOA. One of the Star 3 satellites contains 6 of the NTE retroreflector devices mounted on each external panel of a 1U chassis. The second spacecraft has NTE devices mounted on 3 of the external surfaces and optical retroreflectors on the other 3 surfaces. The third 1U satellite has optical retroreflectors on all 6 of the spacecraft surfaces. The data from this mission, as I mentioned, was used for on-orbit characterization of the passive, of both the passive optical and radar retroreflector devices. The final assembled satellites are shown here on the left. So to conclude, the design and the radar cross-section measurement responses for a passive 1U form factor nanosatellite tracking experiment device is presented here. And although the operating frequency of the NTE devices was targeted for Ku band, other frequency bands may be achieved by modifying the antenna design elements and the corresponding feed network in the system. We're also presently working to design and fly a low size, weight, and power modulated retroreflector payload that provides a unique identification capability for small satellites for improved detection, tracking, and identification for both SSA and space traffic management. So thank you very much, and please feel free to contact me if you have any additional questions about NTE. Thank you.